Hi students, welcome back to lecture number 4 of the Federal Board Chemistry, class 10, chapter number 9. In the previous lectures, we have already discussed about the chemical equilibrium with example and explanation. In the second lecture, we have discussed about the irreversible reactions with their definition, explanation and examples. Now, in the third lecture, we have already discussed about the reversible reaction, their definition, explanation with complete examples. Now we are coming toward the law of mass action. Who proposed the law of mass action? For which purpose this law of mass action was proposed? Generally, the chemist expresses the composition of equilibrium mixture in terms of numerical values. These values actually relates the amount of product to reactant at equilibrium, but these values can be determined by using a relation. What relation? This relation is the law of mass action. This was proposed in 1864 and two chemists C.M. Goldberg and P. Wang proposed this in 1864. Proposed the law of mass action to describe the equilibrium state. And what is the equilibrium state? Now, statement: the rate at which a substance reacts, the rate at which a substance is. Here, the rate also means the speed. The speed at which a substance reacts is directly proportional to the actual mass. The rate at which the reaction proceeds is directly proportional to the product of the active masses of the reactants. Now we are going to explain that what is the active mass. Active mass. These are taken in terms of concentration. These are taken in terms of concentration in mole per decimeter cube. In mole per decimeter cube. Actually, the concentration of the reactants and products are generally represented by brackets. By these brackets. These are not matrices here. These represents the concentration of reactant and products. In both the reactants and product use these two brackets. Now, active mass shows the concentration of reactants and products in terms of mole per decimeter cube for a dilute solution. What is dilute solution? In which water is used as a solvent, not in concentrated form. In which, first of all, we are going to explain the aqueous solution. The solution in which water is used as a solvent is known as aqueous solution. Now we are going to explain the dilute solution. The solution in which the concentration of water is more than the concentration of solute. Or we can also say in which the concentration of solvent is more than the concentration of solute. Actually, this is known as dilute solution. Now, the concentration is expressed in terms of square brackets. Concentration is expressed in terms of square brackets. Again, we are going to clear the concepts of this statement that the rate at which these reactants react with each other, these are actually proceeds toward the product. The rate at which the reaction proceeds is directly proportional to the product of the active masses of the reactants. It means that the amount of product which is formed will be directly proportional to the amount of reactants. Now, we are going to explain this law by a hypothetical reaction, by hypothetical general equation, by hypothetical. Consider a general hypothetical. Consider a general Now consider a general, hypothetical, reaction in which a mole of reactant A and B moles of reactant B reacts, in which A mole of reactant A and B mole of reactant B reacts to give the C mole of reactant C and D mole of reactant of product. These are products. C to give C moles of product C and D moles of product D. It is very simple. There is no any complexity. Now the reaction will be this is C mole, this is product C, this is the mole of the product C, this is the D mole of D. Generally these are A mole react with B mole, in which two reactants A and B react with each other to get the product C and D. What are these? These are the number of moles. These are number of moles. But these are number of moles of reactants A and B, and these are the number of moles of product C and D. That is very simple. There is no any complexity. Now we are going to proceed this general hypothetical reaction. Now the reactant will react with each other and will give the product. So this will show the forward reaction. This will show, actually this will be represented by Kf, and this will arrow which is coming back toward reactants will be shown by Krh, so that the products are coming back towards the reactants and show the reverse reaction. Now the rate of the forward reaction, will be directly proportional. What is this? This is A mole. What is this? This is reactant A. What is this? This is reactant. This is the number of mole of the reactant B. Here is the number of mole of B of the reactant B. So remember that always these moles which lies in the coefficient will coming toward the power, raised to the power. It will be written in power. Now further, the rate of power, reaction, this is K, concentration. The concentration of reactant A raised to the power number of mole of A, concentration of reactant B raised to the power of number of mole of B. Now for reverse reaction. This is just for power reaction. This is for power reaction. Power reaction. Now for reverse reaction, in which the product coming back towards the reaction, as I have already explained in my past lecture to you people, that the reverse sign is used that the product is coming back from the product and that the product coming back towards the reactor. Now for reverse reaction, the concentration will be, the product of concentration will be very simple. Take it easy. The rate of reverse reaction, will be directly proportional to the concentration of reactant C raised to the power number of mole of C and multiplied by the concentration of reactant D raised to the power, actually their mole. What is their mole? D is their mole. Now the rate of reverse reaction will be Kr, concentration of C raised to the power their number of mole, concentration of reactant D raised to the power their mole. Actually these are for the product. These are reactants which are going toward the product for power reaction. These are for power reaction and these are for the reverse reaction. Now further we will continue that the rate that at equilibrium, what happens at equilibrium? The number of power reaction is equal to the number of reverse reaction. At equilibrium, the number of power reaction is just equal to the number of reverse reaction. It is very simple. Now students, you know that the rate of power reaction is this one. This is actually the rate of power reaction. And you know the rate of reverse reaction is this one. Very, very simple. Now we will take these two and written here. Rate of power reaction is equal to the rate of at equilibrium. What happened? The number of power reaction, the rate of the power reaction. Actually, this is the rate. This is the rate. The rate of the power reaction. The rate of the power reaction. This is the rate of the power reaction is equal to the rate of the reverse reaction. Now this is the power reaction, this is the reverse reaction. After rearranging and rearranging, this will be written in a very simple form. Kf divided by Kr, concentration of the product, the concentration of the product divided by the concentration of the reactants. Very simple. Therefore, Kf divided by Kr is equal to Kc. Now, instead of this, we will put Kc here. So this will become as, it implies that Kc will be equal to concentration of D. But here are the number of moles actually. These are here. C, D, A, B. A, B, C, D. This is the concentration of the product divided by the concentration of the reactant. Always remember that the concentration of the product will be written in numerator and the concentration of reactant will be written in the denominator. So what is Kc? Kc is the equilibrium constant. Equilibrium constant. This show the equilibrium constants. Show the equilibrium constant. To this point, if you have any question, you can ask, and that in the next one lecture we will define how you will define the Kc, and we will reflect on the image of the Kc, that what is the Kc and what is the function of the Kc, how it takes part in the reaction. Thank you.